We will talk about one of the most popular computer architecture, MIPS 32. First, we have the introduction to MIPS. MIPS, or microprocessors without interlock byte stages, is a RISC, or stands for Reduced Instruction Set Computer Architecture, developed in the early 1980s at Stanford University, and later commercialized by MIPS Computer Systems. Now we will dig into the key properties of RISCs. First, simple instructions. Each instruction performs a single simple task. Most instructions execute in one clock cycle. Second, load-store architecture. Only load and store instructions access memory. All other instructions operate on registers only. Third, fixed-length instruction, typically 32-bit or 64-bit, simplifies decoding for hardware. Fourth, large number of registers reduces memory access by keeping more data in fast access registers. And last but not least, pipelining friendly, enables execution in pipeline stages like IFID, XMEM, or WB. Now we will come to the main part, MIPS 32 architecture. So MIPS 32 is the 32-bit version of the MIPS architecture. It was designed to be simple and efficient, widely used in teaching and embedded systems. Because MIPS 32 is an RISC architecture, it has all the important features of an RISC. First, the design. Simplified CPU design with a uniform instruction set. All instructions are 32-bit fixed length. Uses a load store architecture to access memory. Next, fixed length instruction. Easier and faster for the CPU to fetch and decode. Compared to CISC, the complex instruction set computer architectures, like x86, which have variable length instructions. Next, load store architecture. Only load and store instructions interact with memory. Other operations, like add or sub, operate on registers only. Next, large register file. 32 general-purpose registers allow efficient data storage, reduces memory access, improving performance. Next, pipelining support. If ID, X, MEM, and WB, multiple instructions execute simultaneously, improving speed. And finally, single-cycle execution. Many RISC instructions execute in one clock cycle, provides predictable performance behavior. Now we will come to the main components of MIPS 32. First, registers in MIPS 32. MIPS uses 32 general-purpose registers from S0 to S31, each 30 bits wide. So you can see these on the screen. We will talk about the arithmetic logic unit, ALU, operations. The syntax of it is first OPT, then OPR, OPR1, and OPR2. So the OPT is the operator or the instruction. The OPR is the destination register where the result is stored. The OPR1 is the first operand register. The OPR2 is the second operand register or immediate value. So here are some basic arithmetic operations. First is addition, or you can write add, subtraction, sub, multiplication, MUL, and division, div. So the example of division, which is a little bit different from the others. So after doing division, the quotient is saved in L and the remainder is saved in HI. So if you want to take the quotient, you must have M floor as T0, or you take the quotient from the L and MFHI as T3, you take the remainder from the HI. So the last problem is handling overflow. So the instructions that detect overflow is add, add, or sub, while the instructions that do not is addu, addu, or sub-u, with u stands for unsigned. So if the number exceeds the 32-bit limit, the result would goes back to 0. Now we will move to the next part, data transfer instructions. So MIPS move data between registers and memory using load or store instructions. First is load and store. Load word or LW loads data from memory into a register. Store word SW stores data from a register into memory. So here's an example. We load A, the th element of the array A, into ST0. So the syntax could be LW ST0 32 SS3. So because SS3 is the base register holding the starting address of array 4. So to access the th element, we have 32 because each word is has the length 4 bytes. The next part is memory storage rules. First is alignment restriction. Memory addresses for storing data must be multiples of the object size. For example, words must start at multiples of 4 bytes. Second is big endian format. MIPS stores multi-byte values starting from the highest order byte. So you can see there's an example below. Finally, loading and storing smaller units. First is byte access. We have LB load byte or SB store byte. So LB is to load a single byte into a register, while SB is store a single byte from register to memory. Here's an example. LB S0 3 S1. So load byte at address S1 plus 3 into S0. Next is half word access. So this is like 2 bytes access. LH or load half, HH store half, where LH loads a 2 byte value and HH stores a 2 byte value. Here's an example that's the same as the above example. Now we move to the next part, logical operations. So logical operations in MIPS 32 manipulate individual bits rather than treating data as a whole integer. So the first part of logical operations is bitwise operations. We have 4 main operations: AND, OR, NOR, and immediate AND. So the syntax could be operation, the destination register where the result is stored, the first operand and the second operand. About AND, it would setting bits to 1 only if both operands have 1 in the same position, 0 otherwise, used for masking specific bits, or perform a bitwise OR, setting bits to 1 if either operand has 1 in a given position, 0 otherwise, useful for setting specific bits. NOR performs a bitwise NOR, returning 1 only if Both operands have 0 in a given position, often used for negation. And immediate AND or AND applies an AND operation using an immediate value instead of a register, enabling quick bit masking. So now we will move to the next part, shift operations. So there are three main operations: shift left logical or SLL, shift right logical SRL, and shift right arithmetic SRA. So the syntax could be the operation, the destination register, the operand, and the number of position we shift. For example, we have SLL, S0, S1, N. So it will shift bits in S1 left by N positions, filling empty with 0. So the effect of it will be multiplication by 2 to the power of N. So for the SRL, it will shift bits right by N positions, filling empty bits with 0. The effect could be division by 2 to the power of N. Finally, for the SRA, the function is similar to SRL but preserves the side bit for side numbers. Okay, so let's talk about branching and loops. Now I will talk about conditional branching in MIPS. So branching allows a program to change its execution flow based on conditions. The three main branch operations are 1. Branch if equal, or BEQ. The syntax could be BEQ T0 T1 label. Function if st1 equals to st0 equals to st1. Execution which jumps to label. So it is used for condition like if x equal to y. Secondly, branch if not equal, or BNE. The syntax is BNE T0 T1 label. So if T0 is not equal to T1, the execution will jumps to label. This is used in conditions like if x is not equal to E. Finally, jump or G. The syntax is G label. So unconditionally jumps to label, changing program flow. It is used for skipping sections of code or looping structures. So you can see there's an example here. So in summary, I will explain this example. So if S3 equals to S4, execution jumps to label if executing clause 1. Otherwise, clause 2 runs and execution jumps to end if to continue. So for loops in MIPS 32, demonstrating how common loops like while, for, and do while are implemented using conditional branch instructions like BEQ or BNE. So loops in MIPS 32 use branching instructions to repeatedly execute a block of code until a condition is met. The provided example follows this structure. I will explain this example. So the loop iterates over an array A, loading each element into T0. The value is added to S1, which maintains a running sum. S3 index E is incremented using S4, and BNE ensures the loop repeats as long as S3 is not equal to S2. So for looping structures in MIPS, the while we will use BNE or BEQ to continue until a condition becomes false. About the for loop, we will use a counter variable y, incremented each iteration, and do while loop, we will execute at least once before checking the condition. So let's move to the comparison operations in MIPS 32. So MIPS 32 does not have explicit comparison instructions like less than, greater than, less than or equal, greater than or equal, but it uses the SLT, set on less than, instruction to derive these comparisons. So the syntax could be SLT T0, T1, T2. The function is set T0 by 1 if T1 is less than T2, otherwise T0 equal to 0. So it is used to check if one value is smaller than another. So for other comparisons like greater than, we would swap operands in SLT and use BNE. For less than or equal, we will use SLT and check equality, and for greater than or equal, we will use swap operands and use BEQ. Example here. So for greater than, we have BNE T0 0 label. So if T0 is not equal to 0, we would jump to label. So the final part is functions and stack. So now I will talk about function calls, which are essential for handling subroutines and managing temporary data. So functions in MIPS32 allow efficient code reuse and modular programming. When calling a function, specific registers handle arguments, return values, and memory management. So for arguments, we have A0 to A3, which used to pass parameters into the function. For return values, we have V0, V1, used to return function output. For local variables, we have S0 to S7, which used to store local data within the function. And return address, we have RA, stores the return location for function execution. So for the function execution instructions, we have jump and link on GAL label, calls the function at label while storing the return address in RA, or jump register GRRA returns the caller function using RA. So last is stack operations. The stack is used to store temporary data, return addresses, and local variables, managed by the stack pointer or SP. It operates using push or store data, saves value onto the stack before calling a function, or pop, restore data, retrieves values from the stack after function execution.